Morning comes from Sinan Kalkan from Middle East Technical University in Ankara in Turkey, and he will be speaking to us about vision, language and manipulation.
Thank you for the introduction. Thank you as well for organizing this nice meeting and allowing me to be part of this meeting. So I will talk about concepts and the things that we have been doing for the last 5 years, some of the old stuff, and I will cut down the old stuff so that I can talk about the new result that we got recently. So let me introduce what we mean by a concept. So when you hear, for example, the word apple, immediately something and a description of an object pops up in your mind. So that description includes the shape of what that object is, for example, the color, the texture, the taste, the sound, the tactile information, etc. So we call that the concept of what an apple is. We use that concept to recognize the different instances of an apple. So, for example, we can recognize this as an apple, another object which we can also recognize as an apple. So they look very different. They have different texture, different color, but the concept of presentation, we can recognize them as an apple. So we call these the instances, and we recognize these instances as the apple object, and the symbol apple, the word apple is the label that we use for the category of apples, and the concept is basically the representation that defines what an apple is. So there are many other words like this. So, for example, we have cup. So we have bowl. These are nouns, or we can be talking about adjectives like thin or soft, and we have verbs like grasp and push. So these basically constitute important constructs in our language, and these are linked to concepts. So when you see or hear the word cup, the cup concept in your brain is activated, what it means to be cup. For example, similarly for an adjective like thin, when you hear or see that word, the corresponding concept is activated in your brain. Not only the concepts are activated when you hear or see the words, they are activated also when you see a cup, for example. So, and when you get other perceptual information from the cup. So the corresponding concept is activated. So we also have concepts for verbs. So when you hear the verb grasp, you immediately activate in your brain what it means to grasp. So we define basically a grasp as an abstraction over lower level motor actions based on their effects. And so this is the direction that we would like to have. So we have concepts which are activated, which are linked to words in language, which are linked to our perception, which are linked to our motor system. And these concepts are also linked to each other, right? Based on their co-occurrences or based on their other relations. And we have too many of them in our brain. So we have a web of such concepts in our brain. So this is the architecture, this is the framework that we would like to put on our robot. So there are many different theories for concepts, what concepts are and how they are represented, etc. So I will talk about just the three main well-accepted theories. The first one is rule-based. So we represent a concept as a set of rules. So this is the rule-based view. And we have, there's the prototype-based view. So we have, in the prototype-based view, we look at statistical distribution of the information in the instances of that category, and we represent that compactly in a prototype. And in the exemplar-based view, we just store all the examples of that category that we have seen up to now, and we use those exemplars to recognize what for example, apple is. So in humans, it is shown that we use different theories for different tasks. So that means we should be probably using a hybrid of them, a combination of them, if you want to implement them in robots. So we will mostly use a prototype-based approach that we have proposed, and we will try to go beyond that. So after this long motivation, let me describe, I will present my research in 3 parts. In the first part, I will talk about the prototype-based conceptualization method that we have been using for the past couple of years. So in this part, I will talk about individual concepts, verb concepts, noun concepts, adjective concepts, and in the second part, I will talk about how we can combine all these concepts. So how can we go to a level where we can talk about a web of concepts instead of individual concepts. Then I will quickly describe how we can define model context in a robot using this concept. So in the first part, I will talk about verb concepts and noun and adjective concepts. So I will just focus on a subset of verb concepts and noun and adjective concepts. So these will not cover every type of verbs, nouns, or adjectives. So regarding the verb concepts, so we define, for example, when you ask the robot to push an object, so you use the pushing verb to ask the robot to satisfy a task. The robot can satisfy that task in many different ways. It can use one of its fingers, 2 of its fingers, etc. So there are many different ways for satisfying the pushing behavior or the push verb. So what we claim is that then the push verb should not be linked to these individual actions. So we should have an abstraction over these actions that can give us this pushing, and we should link the word push to this abstraction. We call that the verb concept. And we achieve that over the effects, the end results of these actions. So we perform clustering of behaviors based on their effects, and we call that the verb concept. I will not go into the details to save time for the new stuff for web of concepts and context. So if you are interested in details, you can have a look at the papers, or we can discuss after my talk. But I will just show the results because they are quite interesting. And regarding noun and adjective concepts, we looked at how we can learn nouns and adjectives. How can the robot learn them? We use the appearance as well as the affordances of the objects. The motivation was that if you look at, for example, these set of objects, they differ a lot in their appearance, but we can correctly classify them as cups. So the main reason for that is that we know their affordances, and affordances is also used for categorizing objects. So the prototype-based conceptualization method that we have been using is quite simple. So we have a category of instances, and let's say we represent each instance as a single feature vector. So we have many of these feature vectors. If you look at the individual dimensions separately, we see that some of the dimensionalities, the changes are, for example, consistently positive. or the dimension itself is consistently positive, and in some of them the dimensions are consistently negative. In some of them we have consistently zero information, or in some of them we have consistently inconsistent distribution. So we can automatically label them, we can automatically categorize them and label them as, for example, plus, negative, minus, 0, and star. So, and then we can represent all the examples using these symbols, so plus, minus, 0, and star. And that is basically the prototype of the exemplars in the so we call that the concept. In addition to the symbols, we also store the mean and variance of each dimension, and we will use that for matching an instance with the prototype. So the advantage of this conceptualization method is that we can easily ignore the irrelevant information. So if you see a star, that means that dimensionality is not important for that category, and you can just use the consistent information, which is plus, minus, and 0, to match an instance and do further reasoning. So here is an example. I will come back to this example again. So for example, in verb concepts, we have the initial features and the final features, and we subtract them, and we look at here at the prototypes extracted from this difference of features. So for example, the pulling verb, the verb pull, causes many inconsistent changes in, for example, surface normal histograms. There are some, it doesn't change many feature dimensions, for example, in curvature. For example, the orientation of the object changes inconsistently when you pull an object, because if you have an elongated object, when you pull it, the orientation of the object changes. But that change is inconsistent. That change is irrelevant for the pulling behavior, pulling verb. The important constant change can be detected easily. That is the change in the position. So with this simple method, we can easily detect, we can easily represent with symbols what it means to pull. So what changes, what is relevant for the pulling behavior, pulling verb, sorry. So that was just an example. Let me introduce the experimental setup and how we did the experiments. Then I will show some results. So we are using the iCub, we have the Connect, we work with the Connect. So we extract some 3D size information, position information, surface normal histogram, curvature histogram, and the presence of the object. So that is the feature vector that we are using. So in the instructions, the robot first sees the initial state of the table. From that we extract the initial features. Then the robot has a set of behaviors. It applies these behaviors on the objects, and it also observes the final state, and that is also a feature vector, and it extracts the final state from the initial state, and that is called the effect feature. And the supervisor gives a sentence about what has happened. So the supervisor says, for example, that the blue ball is pushed, for example. And using cross-situational learning, then iCub is going to link the concepts with these word categories. So in the first part of my talk, we will use these nouns and adjectives. We have these behaviors pushing in different directions, top grasping, side grasping, and we have these effects, basically, which corresponds to verb concepts. So once these interactions are collected, we can train a support vector machine which allows ICAP to predict the effect of a behavior on an object without executing that behavior. So we call that, for example, affordances. So ICAP can predict the affordances of objects by just looking at the object. So without going to the details of how we do the things, let me show just one or two results regarding verb concepts. So since we have a verb concept, since we have a description of what it means to pull, we can show ICAP a few instructions and we can ask ICAP what has happened, what did I just do. So we show the initial state, we apply behavior, and ICAP observes the final state, and from that it should determine what has happened. So the alternatives are no change, the object is moved right, moved left, moved forward, pulled, knocked, grasped, or disappeared. So we compare three different things. First of all, the concept of the prototypes that I've just introduced, where we neglect the irrelevant changes, the irrelevant feature dimensions. And we also had a prototype-based conceptualization method where we don't ignore the irrelevant changes. We don't get rid of the stars. So we include them, and we use Mahalanobis distance, which takes into account the mean and variance of the distributions. And we also had adopted the third prototype, the conceptualization method that I described, just using the exemplars and comparing with the exemplars to determine the category. So for three different instructions, I mean, we have tried more, but just for these examples here, prototype-based method, our prototype-based method performs really well because it gets rid of the irrelevant dimension that can easily detect what has happened, and it performs better than the others. So let me be quick. Let me skip these. These are due to the time constraints. So then we also looked at the learning of adjectives and nouns. So ICAP, using the trained support vector machines, it can predict the affordances of an object by just looking at that. So, and we wondered whether we can learn adjectives and nouns from the affordances and the visual appearance of the object, and whether there is any distinction between nouns and adjectives. And surprisingly, we found some important distinction. So we store the affordance information of the object as a single feature vector. So we have different behaviors, we have different effects. So ICAP can predict the effect of each behavior, and we store that as a single feature vector. So we have more than 50 objects. Let me skip that. So let me show here. So we saw that so the adjectives can be predicted better from the affordances of the objects compared to nouns. So sorry, the adjectives can predict better from the affordances of the objects, and this is the column where we show the results of predicting the adjectives from the appearance of the objects. So if you predict the adjectives from the appearance of the objects, it makes more mistakes. For nouns, we have vice versa. So nouns can be predicted better from the appearance of the objects. So we looked further into that. So we used relief F algorithm to determine the contributions of features for learning the different categories. So for example, for learning the nouns, we can easily analyze the contribution of perceptual features and affordance features, for example. So we saw a very striking difference between adjectives and nouns. So nouns prefer perceptual features, whereas adjectives prefer affordance features. So we first thought that there was a mistake. But then we looked into the literature in psychology, learning adjectives and nouns in children, and we looked at the literature in language on whether there is any distinction between nouns and adjectives, and we found that there is a distinction. So most of the adjectives that we use, noun modifying adjectives, describe only a single change in a single dimensionality. If you have a feature vector that has many dimensionalities, an adjective will usually correspond to only one dimension. For example, height. You have a height dimension. Being tall or short is only described by just a change in a single dimension. Whereas there's going to be many irrelevant information in other dimensionalities. So that is quite difficult to capture by a learning algorithm, and that is actually difficult to learn by children, and we found some supporting evidence for that. So let me continue quickly. So this is, as I mentioned in the beginning of my talk, this is the direction that we would like to go. So we would like to build such a web of concepts linked to language, action, and perception. So we had some initial results on that. So initially, the robot does not have any concepts. Through time, by interacting with the environment, it can create individual concepts, and the concepts that co-occur are linked together in the web. And that gives us we model that as a Markov random field, the web of concepts, and then we use loopy already to make inference. And for example, if ICAP just looks at a single object, it can create this, it can activate the concepts related to the object in its web of concepts. So by just looking at the object, it creates these concepts that is not only related to the noun of the object, but the adjectives as well, and the verbs or the actions that we can apply on the object are activated. Then we modeled context on ICAP using this web of concepts. So we modeled context as a set of active concepts. And we use a topic model, latent allocation, which is used in computational linguistics for modeling context or topic in language. So we have a web of concept, and on top of that, the contexts are basically hidden topic models. So in our experiments, we had 3 contexts: so playroom context, kitchen context, and workshop context. And we just give the robot the number of contexts that there is in its environment, and it can just automatically learn that on top of the web concept. We have these objects, and we distribute them into different contexts. So that ICAP can predict the context very nicely. If there are no objects out of context, it detects the correct context with 100% accuracy. If you add any object that is not from the context, it still detects the correct context. So we can use the context information for improving the detection of objects. Right? So, for example, without context, ICAP can sometimes classify or recognize objects wrong. So, for example, especially the adjectives are really hard to predict, so it makes many mistakes with adjectives especially. But when you put that object into a context, then the mistakes are corrected nicely by using the contextual information. And another important application of having contextual information is planning. So when you make a plan, what you usually do is you look at all the options. So you, for example, do forward chaining to look at all what your behaviors can generate, and you open up a huge tree of possible options. So if you have contextual information, in that tree, you just look at the behaviors that are relevant for your context. So that allows pruning that huge tree and just looking at on a sub part of it. So for example, if you want to push the object from position 5 to 8, and you know that this is a cup, and that is part of the kitchen context, and in the kitchen context, you don't apply some of the behaviors. For example, you don't knock down objects in the kitchen context. So you don't then look at the knockdown behavior in your tree. So that saves us a lot of time by pruning the tree. So let me summarize. So we have been working with concepts for a subset of verbs, nouns, and adjectives. We found some striking results, especially on nouns and adjectives, justifying some findings from psychology and language. So we are still working on going beyond individual concepts. So we are working on web of concepts and what we can do with this web. So one of them was defining or modeling context in this web. And there are still a lot to do regarding that. But yeah, I think I can stop here. Thank you.
Robert, if you'd like to bring those. So, any questions for Sinan? The lady at the back.
Yeah, context. Context can be very subjective.
Yep.
And this is probably because language is also dictated by usage. I come from a Turing test background, and we have hundreds of conversations now between judges and hidden entities. And context is, you're going to have very difficult, it's like the circular problem, definition of words. You define concepts with words. And you get into it. So by the time you've given context to the robot, the concept could have ameliorated, become pejorative. This is a problem.
Okay, we use the words. We use words in shaping the web of concept. That is quite critical. If we don't use words for shaping the web of concepts, then the robot may end up with a different set of concepts that is completely not useful for us. And actually in children, language is very critical for conceptual learning, conceptual development as well. And for context, still it helps because we have too many concepts. We have too many categories. Even if we have words, etc., it's still complicated.
Context can be inside of the person listening or reading. Context is the same.
Sorry?
Context is a similar problem to what you're describing with concept. Because context can also be interpreted subjectively. It can have lots of contextual.
You mean the context can be different from actor to actor?
Yeah.
Okay. Yeah, that's a good point. Yeah.
I think if we any further questions, Sinan, we ask at lunchtime, so that we stay strictly on time.